Hey guys, and welcome back to another Tenfold live show. My name is Philippa and we are here today doing some differential calculus for matric. For those of you who've never tuned into us before, this is Tenfold Live, proudly brought to you by Liberty. We're a show that focuses on matric maths, and we will be bringing you science sometime in the near future. It is every day, Monday to Thursday from 5 to 6 p.m. Also, we have pre-packaged stuff on the content that we're doing, guys. That runs from 4 to 5 every day. So if you feel like you need a little bit of an introduction into the stuff that we're doing, make sure you watch that, because we've compiled some really great content to help you understand what vibe we're trying to get across with our content. Anyway, today we've got some great questions. We're going into the last of our differential calculus questions. Don't forget, guys, next week is analytical geometry. We start analytical, so send in those videos. We love hearing from you. We love trying to help you. I know geometry can be a little bit of a butt ache with you guys, so really send in your questions because we love helping you. For now, we're just going to leap straight into the first question. It's from Ntsako and Jade. Let's see what they need some help with.
Hi Tenfold, I'm Jade from Florida Park High School.
Hi, my name is Ntsako Kutwana Mawela and I'm from Florida Park High.
Please can you help us with this question?
Alright, I really like this question because it's just straight up differentiation, but it also has some little tricks and stuff that you need to try and apply to understand what you're doing in this question. So let's jump right into it because it's really cool. It says, if y is equal to x to the power of 6 minus 1 all squared, prove that dy over dx is equal to 12x to the power of 5 multiplied by the root of y if x is greater than 1. Okay, so we have a lot of information that we need to take in here. Firstly, we need to remember what the initial function is. Secondly, we need to prove that the first derivative of that function is that, and then we need to understand why this needs to be specified. So let's look at this initial function. Firstly, if you're doing AP maths, I know guys, immediately if you see like a whole bracket to a power and you're doing AP maths, you immediately want to do the chain rule. Do not do the chain rule. If you're writing your core maths paper, you need to do this properly without using the chain rule. The chain rule does not apply to normal maths syllabus. So if you use it in your normal maths paper, you are not going to get the marks. Okay, so the first thing we need to do with this question is multiply out that bracket. So that gives us x minus 1, x to the power of 6 minus 1 multiplied by itself. This gives us x to the power of 12 minus 2x to the power of 6 plus 2. Okay, so now we can easily differentiate. So dy over dx is equal to 12x to the power of 11 minus 12x to the power of 5. Oh, look at me making a nice little mistake here. Negative 1 multiplied by itself gives us positive 1. And the derivative of any constant is 0. So this is the first derivative. Now, we're trying to prove that the first derivative is equal to this situation up here. Okay, so we need to try and identify or isolate a 12x to the power of 5. So if I look at this first derivative, 12x to the power of something features in both of these terms. So if I take out 12x to the power of 5 as a common factor, from the first term it gives us x to the power of 6, and the second term it's just once. So we get 12x to the power of 5 multiplied by x to the power of 6 minus 1. Okay, so we have this part of this thing that we need to work out here. Now, let's try and understand where this root y comes from. We were given that y is equal to x to the power of 6 minus 1, all squared. If we square root this y, let's see what happens. We get the square root of this entire expression. And this square root and this square will cancel each other out essentially. So the root of y is equal to x to the power of 6 minus 1. Okay, so if we look here, we see that that's exactly what we have over there, which is really perfect. So we've proven that dy over dx is equal to 12x to the power of 5 multiplied by the root of y. Okay. Now, we've done we've looked at this, we've proven that the first derivative is this. Now we need to understand why it specifically needs to be x greater than 1. Okay, so what we did over here was we square rooted the original y function. Okay, so if we look at this expression here, if x is equal to 1, that whole expression under the square root becomes 0. Okay? And if we had 0, the square root of 0 is equal to 0. So that would mean that 0 goes in there, and that would mean that the first derivative is equal to 0. So that doesn't make sense. Okay, so now let's look at if x was greater than 1. If x becomes greater than 1, then this whole expression here will be positive, and square root of a positive is valid. If x was anything less than 1, guys, that whole expression under the square root becomes negative. And we know that we can't square root a negative number. It becomes an unreal number. Okay, so we specifically needed to say that x is greater than 1, because x can't be 1. That'll make that whole expression 0, and the first derivative is not 0. It needs to have an actual equation. But if x is greater than 1, it means that that whole expression under the square root there becomes valid. It's a real number, because a square root of a positive number is real. Okay, so that's why we had to have x greater than 1, because this root of y is equal to the root of x to the power of 6 minus 1. If x is equal to 1, it becomes 0, and that's invalid. If x is less than 1, it becomes negative, and that's also invalid. So x greater than 1 becomes positive, which means that we have square root of a positive number, and that means that this whole first derivative that we proved over here is a valid number. Okay, so thanks guys so much for this question. Hopefully it helped you understand a little bit more into differentiation, you know, that it can be applied. It's really cool that you can apply differentiation rules to stuff and then still manipulate in terms of the original function. It's a lot of fun to do so sometimes. Anyway, that's for our first question. We're going to jump right into an ad break now, and then Julian will be back for the next question. So make sure you stay tuned, because we've got some great content coming your way.